everybody, this is AP Stats Notes for 4.2 and this is part 1. So on 4.2 we're going to move from doing sampling and surveys to actually experiments. So often when I see the word experiments, I'm thinking of like Phineas and Ferb and Dr. Doofenshmirtz, right? I think that's his name, right? Where it's like this evil scientist messing with people. And actually that's kind of helpful as we're doing notes today. Okay, so let's take a look and get started at what we've got going on today. And that is our notes page for today. All right, so first thing is let's do a comparison between observational studies and experiments. So our first one in our observational studies, we observe and not interfere, right? We're just watching people. Okay, they might fill out a survey for us, but we're just basically watching and gathering information. Okay, there are no attempts to influence results. And we talked about in the last section how that's a bad design, right? That if we do wording to a question, sometimes that'll lead somebody in a different direction, right? So a good observational study does not influence responses, and there is no treatment. Okay, so right now treatment is just a new word, or it's a regular word in everyday language, but we don't know how it works with stats just yet. Okay, let's compare that. And these are not going across, these are just 3 general things about each one. In an experiment, it's that idea of the mad scientist. We're deliberately imposing treatment. Okay, that means we're purposely messing with people, whether that's giving them a drug or having them do jumping jacks or something else. We're purposely influencing them. It's that mad scientist thing of like, we are going to change you somehow or make you do something. Okay, it sometimes has a control group, but it doesn't have to. A good experimental design does. Sometimes uses a control group. Sometimes uses a control group, and if we do an experiment with random assignment, we're going to talk about what that means. If we do a random assignment, we can lead to cause and effect. I'm going to call it causation. Okay, so if all we have to do is this thing called random assignment, and we get this idea that we can do cause and effect. So we gotta pay attention to when we get to random assignment. All right, so the smallest collection of individuals to which treatments are applied are called experimental units. Let me see if I can make this just a little bit smaller. Okay, experimental, that's better. Experimental units, right? These are the things that we are experimenting on. They could be plants, animals, right? Could be people. If we're doing experiments on humans, it's kind of cold to call them experimental units, right? So instead we do the nice warm and fluffy, I'm being sarcastic here, we're going to call them subjects instead. Okay, it doesn't sound that much warmer, but at least it sounds like it's a person. And then a specific condition applied to the individuals is called the treatment. So that thing that the mad scientist does to the people is called the treatment. Okay, the thing that we do that makes it different than just looking at them. Okay. All right, so if an experiment has several different explanatory variables, remember EV and RV are just the beginning part and the ending part, the X that leads to the Y. Okay, a treatment is a combination of specific values of these variables called factors and levels. And these are a lot of words and a lot of vocabulary in part 1. So we want to give you some examples so you kind of know where these things go. So here is our example. Let's say we had 120 pepper plants. Those are going to be our experimental units. They're the things we're going to mess with as an evil scientist. Okay, so we have our experimental units. Our response variable is what we're going to measure at the end, right? The X that leads to the Y. So that's going to be the total yield of peppers in pounds that we get out of this, each one. And then the explanatory variable, we're going to do sunlight. Okay, we're going to change and we're going to mess with them on sunlight. We're going to mess as mad scientists with how much sunlight these plants get. Okay, so half of them are going to get 6 hours of sun, the other half are going to get 12 hours of sun. So I drew a little bit of a diagram, right? So here's my plot of where I'm going to put 60 pepper plants, and they're going to get 6 hours of sun, and the ones over here are going to get 12 hours of sun. So our treatments are the amount of sun that we're giving to these plants. So we have two treatments. Either they're getting 6 hours or they're getting 12 hours. Experimental units are the plants themselves. Explanatory variables are the thing that is leading to the other thing, right? So the X that leads to the Y. So does sunlight lead to higher yield? So sunlight is the EV, the explanatory variable. The response is how much weight of the peppers do we get from this? Okay, and now we're adding in a third one is what's the treatment? What are we doing? We're doing two different treatments. We're applying 6 hours of sunlight to some of the plants, and the other half are going to get 12 hours of sunlight. Okay, all right. But what if we also wanted to see if fertilizer could help as well? So in addition, we're not going to give up the sunlight. We still want to do the 6 and 12 hours of sunlight. So now we want to do 3 different fertilizer types. So 1/3 of the plants are going to get fertilizer every day. The next third are going to get it every other day. And then the final third won't get fertilizer at all. So now the plot is going to look a little bit different. Instead of it just having 2 sides to it, it's still got those 2 sides, except now we've got 3 different categories vertically as well. We've got fertilizer every day, every other day, or no fertilizer. Okay, so what has really changed here? So let's go and think about this. Our experimental units are still the same, 120 pepper plants. Our explanatory variable has now changed though, right? We have 2. Before it was just sunlight, now we have sunlight and fertilizer. Okay, and sometimes they'll call experimental variables factors, especially when there's more than one. So they'll say like there's 2 factors to this experiment. They're really just saying it's 2 experimental units, okay? And then what goes after that? The response variable hasn't changed. We're still measuring yield of the pepper plants. So then we're down to what's the experiment itself? What's the treatments? Well, overall, I can see in this category here, if I count them all up, there's 1, 2, 3, 4, 5, 6 different treatments that I'm keeping track of. So I already know that the total is going to be 6 treatments. So we want to be able to explain to people, like we're doing sunlight and we're doing fertilizer. The sunlight only has 2 different levels to it, either 6 or 12. The fertilizer has 3 different levels to it. It's either every day, every other day, or none. Those are called levels. So we would say that there are 2 levels of sunlight and there are 3 levels of fertilizer. Okay, so for a grand total of 6 treatments. So a lot of people will misuse all of that vocabulary. So there's a good example for you to go back to and look at. Okay, so factors are sometimes explanatory units. Levels are when you're actually spreading things out into different groups. So when we did sunlight, we actually did 2 levels at the beginning, okay, and then we added in 3 levels of fertilizer. And then if you multiply those together or count up the number of boxes there would be, that's going to be your number of treatments. Cool. Let's go and practice some of these. So in here it's going to say state the experimental units, the explanatory unit, or experimental units, the explanatory and the response variable, and then the treatments. Okay, so I'm going to color code these so that they're easy to spot. Okay, so when I'm reading through this, remember that the experimental units are the who or the what, right? Who are we testing or what are we testing? Okay, and when we're looking for experimental units, we're thinking about what is the thing that we think is leading to the Y value, right? And then the treatments are that evil scientists. What are we doing to mess with this design? So mess with the who or the what. All right, so when I read through, I want to be very careful that if I can pick out who it is that they're actually testing and recording results from. Okay, so let's read. So we've got 14 middle schools were recruited to test a new teaching method called Career Start. 7 schools chosen randomly used Career Start with a regular curriculum, while the other 7 used the regular curriculum without it. Both groups were followed for several years, collecting data on student attendance, behavior, standardized test scores, level of engagement, and whether or not the students graduated. Okay, nowhere in here did it tell us number of students. They're talking about schools being tested. So those are my experimental units. It's the who or the what. So we're going to say that the experimental units, I'm just abbreviating here. This is not technically the best way to abbreviate. I'm just making it easier so I have a little bit more room. So experimental units in this one would be the 14 middle schools. All right, the thing that we're testing, right? What are we seeing if something affects something? We're seeing if this career start has some effect, right? So we're checking out the Career Start program. All right, and we're seeing if the Career Start program has something to do with, okay, how are we going to determine success or failure about this Career Start program? That's all those things they listed with the commas in between. So that is attendance, I think they said, attendance, behavior, standardized test scores, and level of engagement. And then something about graduation. Okay, those were all the things that they were measuring to see if this was going to be a success or not. All right, so last thing is, what are the treatments? I'm going to use TR for the treatments. So basically, we really only divided people into two groups. They either got Career Start or they didn't get Career Start. So that is 2 treatments. And the 2 treatments are with Career Start, and without Career Start. Cool. Okay, that's all our 4. So let's go do another one. All right, so this one is going to be 2 medicines, and that's usually what we think about when we hear a experiment coming our way. So let me go and switch over to looking for experimental units. So we're looking at 2 medicines to determine the effectiveness of treating head lice. Their choices of treating it are either an oral medication, a pill that they take, or a lotion that they have to put on. Researchers studied 812 people in 376 households. Okay, so right now I'm thinking it's either people or households. I'm going to keep reading to see how they're testing them. Are they testing people or households? Okay, so from 7 areas around the world. Of the 108, there we go, of the 185 households. So there is my experimental units. It is the 185 households. That's how they are planning to group them to test them. So the 185 households randomly assigned to oral medication. So we're trying to see if medicine will affect the treatment or the number of lice present after a certain time frame, I guess. So our EV, our explanatory variable, is the 2 medicines, right? Will the 2 medicines work? Will either of the 2 medicines work? So the 2 medicines are the oral or topical. Okay, and then the response variable, what are we hoping to measure at the end to determine whether this is a success or not? How about the measure of success is the measure of, let's see, how would I say this? The measure of success is the percentage of households that are lice-free, maybe? Okay, hopefully they're not going to count every lice. They'll just come back and say, hey, it worked in this household, not in that one. All right, and then the treatments. So the treatments, are you noticing, are often very close to the EV, right? We're trying to apply the treatments and see if there's an answer. So my treatments are the 2 medicines again, oral and topical. All right, pretty easy. Let's try that one more time. So, oh, this one sounds familiar to the one we just did with pepper plants. Here we go. Does adding fertilizer affect the productivity of tomato plants? Right there, we've got almost everything we need. Experimental units are tomato plants. We're trying to see, does fertilizer, that's my experimental variable, affect productivity? So some kind of, good response of plants. And then my treatment is the fertilizer. So we're going to read ahead to see how they're doing fertilizer. The gardener plants 24 similar tomato plants in identical plots in a greenhouse. So I'm taking that to mean they're taking 24 and splitting them up possibly. So I'm saying their experimental units are 24 tomato plants. 24 tomato plants. Our experimental units, our experimental variable, explanatory variable, sorry. Our explanatory variable is what are we going to be testing? So far it's fertilizer, right? Okay, response variable. So let's keep reading here. He'll add fertilizer in the soil in half the plots. So it's either going to be fertilizer or what? Probably it looks like no fertilizer. So fertilizer or no fertilizer. But then they say also he will add water. What? Okay, so now we've got another one. We've got fertilizer and water is our two explanatory variables. So water. So now we have two things that could affect how that tomato plant grows, fertilizer and water. What are we hoping to see at the end? So this would be the productivity, and let's see, they said at the end of 3 months, you'll record total weight. So total weight of tomatoes. Okay, so now here we go with what is the treatment. So we know our treatment is that we are using fertilizer and water, but this is where we can talk about how they were separated, okay? So fertilizer had two different levels, right? So I could say that these are two factors. Water and fertilizer are two factors, okay? And then we have, let's do it this way, fertilizer. They did two types, right? They either got it or they didn't, right? So there were two, what do we say for types? We say two levels, right? So there were two levels. They either got it or they didn't. Okay, with water, we had, let's see, looks like 1 gallon of water per day, 1.5 gallons. Oh, and it's missing this. Another 8 will get 0.5 gallons per day. So we've got three different levels of water. And those three different levels are either 1.5 gallons per day, 1 gallon per day, or 0.5 gallons per day. It's not in the problem, but it should have been. So that's a mistake on my part. All right. All right, last thing we're going to do is when two variables are associated in such a way that their effects on a response variable cannot be distinguished from each other, we call that confounding. So let's give you an example for this so you know what the word confounding means. Okay, so a while back there was a humongous court case about whether tobacco products and specifically like cigarettes cause cancer, right? So the idea here was the EV was, do cigarettes cause cancer? RV, cancer. And so what did the cigarette and the tobacco companies say? They said, oh no, it's not our product causing cancer, it's what? What else were they trying to blame? They were trying to blame it's the environment, it's their food intake, it's the medicine they're taking, maybe it's their other health issues they have. You can't tell me it is specifically other health issues that they have. You can't tell me it is specifically cigarettes. So the confounding factors in here are all of these. Okay, if we can't show it directly, it's like what other stuff is interrupting our process of going directly from cigarettes to cancer? What else is in the way? And that's it for this first part. Bye, guys.